Alright, there's number 33, 20 liters. They give you the moles, 5.6, gas constant, 0.0821, 128 Celsius plus 273 is temperature, 9.4 is ATM, PV equals nRT. So you're just plugging in the numbers they give you for number 33. This one was supposed to be pretty easy because they give you everything you need. You just plug it in and solve for me. Okay?
Why the heck did they write 2.0 when they could just write 20?
Sig figs. That's 2 sig figs, 2.0. So 2 sig figs, 3 sig figs, 3 and 2. So
Okay.
2 sig figs is what you round, that's why. Okay, 47. Alright. So 47. Bless you. 54.4 grams per mole. So they give us the density, right? Yeah, so the density is 4.65. Okay, so they don't give us the density. So, okay, here's what they did. They use that density equals the Pimpin' Mama over Rocket Tiger. That's what they use. So they use density equals P, in case you're confused. They use this. MM over RT, and then they rearranged it. Okay, but there's another way you could do it. All right. So they give you the. Let's see. They give you the volume. They give you the pressure. They give you the temperature. You could solve for moles. Okay, that's another way you could do this problem, right? So you could take. PV equals nRT. So your pressure is what? 1 ATM. Your volume is, what is it again? 2.1. 0.0821 over, what's the temperature? 300? Yeah, 300. So if you do that, you solve for moles. Did anyone do it that way? What'd you get for moles? 0.188. Okay? Molar mass is grams per mole. So now you take that 0.465 and do 4.65 divided by 0.188. That's grams per mole, and that should give you 54.1. It doesn't?
0.85.
Okay, so this number is not 0.188?
I don't believe so.
Okay. It's just 2.1 divided by these numbers multiplied. So you got what?
0.085.
0.085 moles. Cal, you got that? Anyone else get that?
Yeah.
Okay. 0.085 moles. So when you divide 4.65 by that, you should get 54.4 or something close to that. Okay, so this is just if you remember that equation. This density equals pressure times molar mass over RT is not on the equation sheet. Your PV equals nRT is. So you don't need to use that equation. There's always a way to do these without it. All right, so that's 47. You good, Skylar?
Yeah.
Just made a simple mistake.
Yeah.
All right, 49. Let's see. Where's 49? Where are the numbers of the problems? There it is. Okay. All right, so I might have to back this out here. All right, so let's see. 49. They have 64% carbon. All right, so at once, so they give us. All right, this one's complicated. They give us Celsius, we need to convert that to Kelvin. They give us millimeters of mercury, you got to convert that to ATM. Why? Because you can't use the gas constant. This is liters, ATM, Kelvin, mole, right? So I made a point to kind of say what's the unit yesterday when we were learning this, because this can only be used with ATM. So if they give you millimeters of mercury or torrents or kPa, anything, you got to convert to ATM. They give you the mass, which is 2.3. What is the molecular formula? Okay. All right, so I'll just show you what they have here. So to calculate the empirical formula, you have to turn all your percents to grams. This is just review from before. So when you get all your moles, you get moles of carbon, oxygen, and hydrogen. If you divide by the lowest number, which is oxygen, you get C4H10O. All All right, so there's your empirical, C4H10O. The reason they do that is now you take the numbers they give you and you can calculate the molar mass. If you get the molar mass using basically just like the last problem. The last problem we did the same thing. We found the molar mass. So now if you know the empirical, and that has a mass, 4 times 12 plus 10 plus 16. Once you get the molar mass, depending on how much larger it is, you know what to multiply those by, and that's how you get your answer. So that's the gist of it. Here's the work. So you got to convert millimeters of mercury to ATM. There's 760 millimeters of mercury in 1 ATM. You have 750. So X. Some of you prefer the proportion, so there's a proportion, but this is another way to do it. It's just 750 divided by 760. Cancel those out. You get ATM. They told you 1 liter. You know the gas constant. Temperature is easy. Just add 273. So what you're solving for is moles. So once you convert to ATM, you can plug it in for P. Your moles 0.0306. Grams per mole is molar mass, right? 2.3 divided by what you just found, 75. So this has a mass, let's see, 4 times 12 is 48. That's 58 and 16, which is 74 grams per mole. Yeah, 74 grams per mole. So that's pretty close to 75. So basically, it's the same. Okay. So the formula, it's supposed to be pretty. It's supposed to. If you were probably to keep all the decimal points, it would be pretty close to 75. So the molecular formula is the empirical. So the answer to this question, C4H10O. So this question takes what we learned before with empirical formulas, right? So, where'd I go? Sorry. Where did I go? Oh, right here. So to take, the percent, turn it to grams, get your empirical, then apply the new PV equals nRT. Who got that? 1.5, half a person? Did you guys find the empirical, or did you just not know what to do? Okay, so yeah, when it's asking for the molecular formula, right, is that what it says? Yeah, molecular. I guess the biggest problem with this is like, where do you start in your brain, right? How do you understand where to begin? So if they're going to ask for a molecular, the only way you can get a molecular is if you know the empirical first. Then you multiply it by whatever you need to reach the mass of the molecular. So anyways, that's how you do it. All right, that says method 1. Do they give us a method 2? Yeah, let's see, what do they do here? All right, so they calculate the moles, then the molar mass. Next, multiply the mass. Oh, okay, I see what they did. So the second method, they calculated the molar mass first, so that's the same calculation as before. And then they took the percentage and multiplied it by the molar mass. That makes sense. So if you know the grams of the total, and you multiply by percentage, you'll get the grams of the individual atoms, right? So that's grams, this calculation is grams of carbon, grams of hydrogen, grams of oxygen, and then they turned it to moles using the molar mass, then divide by the lowest number. That's another way to do it. Yeah, I probably would have done it the first way if I didn't look at it, but maybe that makes sense to you guys. So hopefully one of those things makes sense to you. All right, so that's 49. 105. All right, so 105, where are we? All right, baking soda, blah, blah, blah. All right, so you have to turn your 5 grams of baking soda into moles. The ratio between baking soda and CO2 is 1 to 1. So you kind of needed to know, I guess, the equation, right? Sodium bicarbonate, when it's heated, releases oxygen gas. So I think they probably show you the overall equation. Let's see, what is it again? 105, right? All right, so yeah, there's the equation. Oh, I'm sorry, it's 2 to 1. See, I didn't write out the equation. I was doing it in my head. So yeah, baking soda breaks down. Did we write this equation on our equation sheet? Take it out. If not, make sure you get this down. You should know the decomposition of baking soda. This should be on our equation sheet. Remember, you're going to keep this all year. We did, okay? Keep this all year, so at the end of the year we can review it, right? Because again, I don't really teach specific reactions. We do enough problems all year where they just pop up. So we just compile them. So baking soda always produces CO2. How do we know that? What did I tell you? What's the trick? What reactant will always produce CO2? Or what part of a reactant? The carbonate ion, CO3. You see CO3 in a reactant, literally like 99% of the time you're going to get CO2. Okay? So these are your products. It's a 2-to-1 ratio. Turn your moles of grams of baking soda into moles of baking soda, and then you would divide that by 2, right? So whatever this number is, okay, right here, 5 divided by 84, they do it all in one step. So 5 divided by 84 is moles of this. Well, this is half, right? Half the moles of this will be produced. And do they give us that number? Let's see. So moles of CO2, 0.03. That part, if you knew this, everyone here should be able to do this. So if you didn't have this, or you didn't look it up, or you didn't write it down, then you probably had trouble. So at least right now, seeing the balanced equation, you should be able to that should make sense, right? You should be able to do that at this point. 0.03 moles. We know the temperature. All we need is volume, right? PV equals nRT. All right, moles goes here, 0.03, 0.0821, 453 Kelvin, divide by pressure, and you get 0.86 liters for letter A. 0.86. So the hardest part probably was figuring out what the balanced equation was, but then once you had that, it's just stuff we've been doing. So stoichiometry, kind of like that demonstration. Exact same concept, except we didn't react with acid. So anyways, 0.86 liters. So there's that. Part B, what is it asking? Ammonium carbonate. Okay. One advantage and one disadvantage of using ammonium carbonate instead of sodium. Ammonium hydrogen carbonate. Okay. Let's see. Ben, what do you think? You got anything? One advantage or disadvantage?
An advantage would be the absolute solubility of NH4+.
Okay. Any disadvantages?
An increase in H+ donation.
Okay. Anybody else got something? Paige, you got anything? Anybody? Well, we don't use ammonium bicarbonate, right? In cooking, we use sodium. So you would have had to look that up. We don't want ammonia gas in our biscuits, okay, or whatever people are making, okay. You don't want to eat ammonia gas or breathe it in or produce it in your house. So if you didn't know this, then obviously you couldn't answer this. All right. So that's the negative part. Okay. Advantage is that there's more gas produced because it's a 1-to-1 ratio. So I don't know if that's necessarily. I don't like this question. They're trying to like make it like a real question. Sometimes they stretch. I don't like this, but because there's 1 mole, so whatever you use here, you're going to make the same amount of CO2 because it's 1-to-1. That's the advantage. But let's not eat ammonia gas, right? So that's not good. All right, 118. Here we go. And we'll do the dilution problem and move on. All right, 118. Here we go. 118. Looks like the answer is 1.58 times 10 to the 4th liters. Okay. Well, let's see. What was the question asking? Commercially, compressed oxygen is sold in metal cylinders. 120 liters filled with oxygen with pressure 132 atm. That's crazy. What is the mass of oxygen present? All right. So yeah, you use PV equals nRT. This should not have been a hard problem. I hope not. They give you everything you need. You solve for moles. You know the molar mass is 32, right? So if you know the moles, multiplied by the molar mass, moles cancel, you get grams, which is about 21,000 grams of oxygen. Right? That's a huge number, 654 moles. So now it says, that's part A, I guess. The first part, how many liters of oxygen gas at 1 atm and 22 Celsius could the cylinder produce? Assume ideal behavior. They tell you that so you can use the ideal gas equation. You know the moles, you know the gas constant, temperature they gave you, and pressure. So again, both of these are typical AP questions. Shouldn't have been hard for you. Okay, so if they were hard, I'm not trying to make you feel bad, but there isn't a whole lot of figuring out. You're just plugging numbers in and then doing some simple calculations. So it was 2.09 times 10 to the 4th grams, and then 1.58 times 10 to the 4th liters. All right. Anything you want me to clarify or go over again? Okay, the dilution problem. All right. Let's see. Does anyone know the answer to A? How about our friend Luke?
142.
Questionnaire was talking about sig fig. Hey.
No. See, I don't even know what the question was asking. It asked like 3 different things.
This is the kind of stuff the AP test does. It'll take something that you should know, and it's not that hard, right? Dilution question, and then they ask something squirrely, right? So the balance used to measure the mass. So all you want to do, it's a very simple concept, is take 0.1420 grams of solid sodium sulfate, and you want to dissolve it to a dilution of 0.01 moles per liter, and you need 100 milliliters. So that's it. You're just making a solution. Very simple. Mass this out, put it in volumetric flask, fill it up to the line, shake it up so it dissolves, and you're done. It's like, it is a very simple concept, but they make it complicated. The balance used to measure must have a certain minimum level of precision to ensure that the concentration can be known to 4 sig figs. If this minimum level of precision of the balance is expressed as plus or minus X milligrams, what is the value of X? In other words, what does the scale need to show to have at least 4 sig figs? If we have a scale that goes out to 2 decimal places, what's the max number of sig figs? 3. This one, and this one. Think of a number like, I'll make up a simple number, 2.52. If that scale on the back, which that is the best I have out right now, the best the scales over on the left can do is 3 significant figures. So that's plus or minus, that would be plus or minus 0.01. That's the scale I have in the back, but that only gives us 3 sig figs. So what would the answer
Where'd
be?
you get the 0.01 from?
So I'm just making that up. So
Okay.
it could technically be 0.00, but that doesn't have a number. So I know it's hard for me to explain this. It's just something you kind of just, like if you take college chem and you do more, measurements on scales that are very small amounts of things, you just get more used to this. But so that's just, the 0.01 is just like the standard way of a company who makes scales, or chemists, or physicists to explain the precision of a scale. So like a scale that goes out to the tenths would be 0.1, plus or minus 0.1 milligrams. If it goes out to the hundredths, it would be plus or minus 0.01. If it goes out to the thousandths, 0.001. So that's just like a standard number you use to say, this scale goes out 3 decimal places, this goes out 2, this goes out 1. This could give me 2 sig figs at most, this could give me 3, this could give me 4. So that's the answer. 0.001 is X. I give you these problems so you understand, hopefully, in the future. It isn't something I'm really expecting you to fully get, right? Remember, a lot of these problems is to practice and learn, and so you can do well in the future, not to get it right that moment. So 0.001 is how you would write that, all right? So that's the precision. Does that make a little more sense?
Not really.
Really?
It's a little bit, but
It's just, all this number is saying the scale needs to go out to the 3 decimal places. That's all that's the only way you can have 4 sig figs. That's it. They give you a lot of information, but the last sentence is the most important part. If this minimum level, what's that, 4 sig figs, is needed, what would the the precision be expressed to. You just have never seen anything like this before. Okay, so we're gonna move on. That's kind of minor stuff here. All right, if you can do this problem here, you're in much better place. If you can't do that, I don't really care that much. This is way more important, just to put it in perspective. All right, B. Okay, Nicole, what do we got? On the left side there, you got burette, volumetric flask, 100 milliliter beaker, squeeze bottle. Did you use any of those? You circled the squeeze bottle. Good. What about the middle? Skylar, got anything? So the 100 milliliter volumetric flask. Okay. Anybody use anything on the right side? Which one, Paige? Distilled water. Is that all you guys circled? The squeeze bottle, 100 milliliter volumetric flask, and this distilled water. Is that all you need? You're going to use the 10 milliliter volumetric pipette? Okay. And the volumetric flask? Let's just use one of them. The volumetric flask is extremely accurate, so you don't need the volumetric pipette. So that volumetric flask I showed you the other day with the line on it, it's extremely accurate. I would say I would need the dropper though. Why would I need the dropper? You guys would too. If I need it, you need it. What's that? What'd she say? I didn't hear you. So, what did I do with the dilution the other day? I screwed up. What'd I do? Filled it way over the line. So I was just hurrying up for this example, okay? But once you get close to that line, you would stop, and then you would take a dropper and add distilled water drop by drop until the meniscus was right on the line. So the way you would answer this on an AP test, you would circle the circle the squeeze bottle, circle 100 milliliter volumetric flask, you would circle distilled water, circle the dropper, and then there'd be like an answer booklet, and then on the lines you would say, let's see. You would mass the solid Na2SO4 using 4 significant figures to 0.1420 grams. So you would really spell it out. All right. And then, what would you do with the solid? Would you put it to the side, or would you put it in the volumetric flask? Because the rookie mistake would be leave the solid in whatever you measured it in. Take your volumetric flask, fill it up to the line, and then put the solid in. What's wrong with that? It'll go above the line because the solid takes up space, right? So you always put your solid in first, then you put your solution, your water in, because the volume's already taken into account, right? So you would say, again, after you measured it out, you would put the solid in the volumetric flask. And here, the best way to do this is you fill your volumetric flask halfway. You swirl it, dissolve all the solid, then you would fill it up with water to the line with the meniscus right on the mark, cap it, you would invert it like 4 or 5 times, and then you're done. That's like how you're supposed to do it. If I'm going to show you exactly how to do it, that's how you would do it. So that's how you would answer that question. All right. We want those kinds of questions because you can get those. You just have to think about what you're doing. And I may not ever have you make a solution. I kind of showed you, but that's how you would do it. It's probably better to have you guys make one. But anyways, that's how we do that one. All right. That was it for homework, right?
Yeah.
Labs. Okay, we're good. Take out your notes.
Thought we were gonna go back.
What are we doing?
Back.
The back of what?
Question.
What, the multiple choice?
Over.
Yeah, keep those. Keep those out. We're going to get to those in a second. All right, this problem is due Monday.
Oh my god.
Okay, write this down. You're going to have more than this, too. All right.
I have a tournament this weekend.
Let's see, 130 here. Okay. So, all right, here's the question. Write it down, please. I don't care where you write it, but you got to do this for Monday. All right. Nitrogen forms several gaseous oxides. What that means is nitrogen bonds with oxygen, and there's like a few different ways it can form. So the common nitrogen compounds here. Nitrogen forms, what did I say? Several gaseous oxides. It forms NO2,
Gas.
Tristan's favorite, N2O, N2O5, I think it forms N2O4. There might be another one I'm forgetting. So those are your those are your options. One of them has a density of 1.33 grams per liter. So one of those. Measured at 764 millimeters of mercury at 150 degrees. Calculate the formula.
Slow down, say that again.
Which part?
Starting at the one something,
One of these compounds
okay.
has this density, this pressure, and that temperature. Calculate which one it is. What formula is correct. And I could be wrong. It could be one that I can't remember that is the answer. But it's something with nitrogen and oxygen. You have to take the data I gave you, figure out the subscripts. You did 2 problems like that for home. I just went over them, so you should have at least a fighting chance. Alright, I wanted to give that to you yesterday, but I couldn't find it. So I found it, so there you go. Okay? Can't erase those? We're good?
So, yeah, what are we finding for it?
The formula. So this is, look, it's N question mark, O question mark, right? You're looking for these subscripts based on these numbers. So you're going to have to use PV equals nRT
Do
and
you want like the molecular or like the empirical or?
it's molecular. Because when you solve for molar mass, so if you get moles, right? So if you find the moles using PV equals nRT and you do grams per mole, that'll give you the molar mass, and that's always the actual formula. That's the actual mass of the molecular. That's never going to give you an empirical molar mass. That make sense?
Yeah.
Okay. All right, here we go. Let's look at the multiple choice. What we did 3 and 4. We were talking about 5, right?
I answered 5, but you got 3 spin. Because I got it right, but.
All right. Let me kill this thing here. All right. So, where are Liz and Taylor again?
Field trip.
Yeah, where'd they go?
Close.
Oh, yeah. All right. Number 5, classic AP question. Now, the good news for you guys is I kind of redid my quizzes and tests and I redid all my stuff when the curriculum changed a little while, like 4 years ago, 3 years ago, something like that, 4 years ago. The reason I'm telling you this is some of my questions, like this here, these 5 questions, are the old format with 5 choices. The new one is only 4 choice, multiple choice, which is way better. That significantly helps students. Whenever you take a test with 5 choices, it's like a kick in the face because it's a whoa, it was aggressive sneezing.
I'm sorry.
That's okay, it happens. So it's good you don't have to deal with that 5th answer. It's really annoying. So this is harder than you would have to do, on an actual test. But anyways, this is classic. You will have a limiting question, multiple limiting questions on the AP test. This is just one type. All right, this is worth going over fairly slow because you need to be able to do this without a calculator. Okay? Remember, Tuesday's quiz, part of it's multiple choice, no calculator. Part of it's short answer, you can use a calculator. Okay, so just keep that in mind. So, now how are you supposed to do this without a calculator? All right, it says what mass of HF, right? So what mass, so grams, by 3.0 times 10 to the 23rd molecules of those. How many moles is that? Someone just said. 0.5. That's what everyone needs to be able to do, like, off the top of your head. If you can't do that, well, you got to get there. Okay, you got to get there. You need to remember Avogadro's number. 6.022 times 10 to the 23rd is 1 mole of anything in the world. So if you have half of Avogadro's number, you have half the particles, which means half a mole. It's a 1 to 2 ratio. So if you have 0.5 moles of that, that's going to give you 1 mole of that. So this tells me I'm going to make 1 mole of HF. This is excess. It told us that, so no one cares about that. The moles of this will directly affect the moles of that. since it's a 1-to-2 ratio, however much you use here, you're going to produce twice as much. So you're producing 1 mole of HF. Well, what is the mass of 1 mole? The mass of 1 mole of anything is just the mass from the chart, the molar mass. So 19 plus 1 is 20 grams in 1 mole. And that's why the answer was D. So you got it right, luckily, I guess.
No,
But
I skipped all of that and I was like, okay,
right.
to add the 8.
So you got lucky. If this was a 1-to-1 ratio, what would the answer be? 10, right? Because 1 mole is 20 grams, so 10 moles would be half. Or sorry, half a mole would be 10 grams. Okay, so if it was 1-to-1 and you still did that, you would have been off, obviously. So that's how you do these problems. They're not going to give you some weird, crazy number. It's going to be 0.5, 0.25, 1, 1.5, 2. It's going to be numbers you can do in your head or on paper. And then you just have to do a simple 1 to 2. Sometimes it's 1 to 3. You know, so, or if it was like 0.33 moles, right, and it was a 1 to 3 ratio and you triple it, you know, it's going to be numbers you can handle. Because kids get all stressed out. I can't use a calculator. That's all right. You're smart enough, you can figure it out. Just take your time, look at it, and see what you need to do. Okay. Did you try 6 or 7 at all?
Yeah. 6.
All right, let's talk about 6, and then I want to give you a little notes here. At least one problem, hopefully. All right, what is the total number of moles react and consume when 1 mole of CO2 is produced? All right, so it's a 1 to 3 ratio, right? For the what is that? C3H8. What's that called? What's the prefix for 3 carbons? You guys remember? It's meth, F, U. It's 4.
Wait. Matt?
That's propane. That's propane. It's an alkane single bonds. You can draw them out to figure it out. It's 1 to 3, right? So you have 1 C3H8 equals 3 CO2, and you have 5 O2, which equals 3 CO2. So the question wants to know, what is the total number of moles of reactant? So right now it's 6. But it's saying, what if we produce 1 mole? So instead of 3, we're producing 1. So if it's 1 to 3, x to 1, that's for this one. And if it's 5 to 3, it's x to 1. Right? So this is going to be 1 divided by 3 equals x, right? So that's this one. So the answer is 1/3. So 1/3 of the moles here. And then for oxygen, it's going to be x equals 5 divided by 3, right? That's going to be your oxygen. So it's 1/3 plus 5/3, which equals 6/3, which equals 2. Do you see how I made a complicated problem easy? This is why I do this in practice. If you try and make this 0.333, because you know that, and then you try and turn this to a decimal, you're going to get all screwed up. And maybe you can do it in your head. Maybe you can write that decimal, and if you can, great. But I prefer, with these types of problems, to leave it in fraction form, because it's a heck of a lot easier for me to say, okay, 6/3 is 2. Instead of 0.333 plus whatever that is, which would obviously be 1.667.
How'd you get the whole thing to add them together? Like, where did that come in?
Because it says what is the total number of moles of reactants. So if I take the new proportions, right? Instead of 3, we have 1.
Yeah.
So if I do each one, I realize I need 1/3 of the C3H8 and I need 5/3 of the O2. I need to add those together because the total number of moles would be oxygen plus C3H8.
Okay.
So that's how you do, again, that's how you get around. It looks like it's hard. How do I do this without a calculator? Keep it in fraction form. Okay? Alright. I'm like between a rock and a hard place here. Alright, keep that. We'll go over 7 on Monday. I'm just going to give you homework anyway.
Just gave us that question.
It's one question. You have nothing else going on in this class right now, right? Nothing else to work on. Oh, wait, problem set. You always have a problem set. That's like the sun always rises, so whatever. Alright, so did I give you alright, so let's do 54. Chapter 5, number 54. I think these are stoichiometry problems. Yeah. So 54, 62. Ooh, 62. Have fun with that one.
What page is this?
Chapter 5.
What page?
Just 218. It doesn't matter. Go to chapter 5. And then. Alright, I'll just give you those 3 problems. Alright? So, the problem I wrote on the board, or the one I said out loud, make sure you know what to do, listen up. The one I wrote on the board, 54 and 62. I have other ones, we'll do those next week. Okay? Real quick, hold on, don't pack it up. Those 2 problems, so 54 and 62, are stoichiometry problems. So you have to find limiting, then find your products, then use PV equals nRT to do whatever it's asking. Okay? Kind of like that one we did on the homework already. So, alright, so that's 54 and 62. And then don't forget the other problem. So let's do Monday. When's your problem set due?
Thursday?
It's due next Thursday?
Thursday, Friday, I don't know.
Due Thursday. Problem set number 2. Anybody look at it yet? There's a lot of work you need to do. Do not wait until Wednesday or you're going to be screwed. What?
Oh,
Yeah, it's due Thursday. So it's some of it's not like hard. You can do it, but it's just a lot. So just keep that in mind.